next talk is by Pierre-Francois Rodriguez, back before.
Okay, so thank you. So thank you to the organizers. Codina is their representative for the organization of the workshop and for the opportunity to speak. So I'm going to talk about a percolation problem, but it's in fact percolation that involves random walk. So hopefully it will be something that many of the people in this audience will feel close to and will recognize things that they're well familiar with. So let me start by giving you a setup. So I'm going to assume that I have a graph G, and maybe it's even a weighted graph. And so I'm going to make assumptions on this graph soon enough, but let me not do that until I have to. So the only assumption I'm going to make for now is that it's transient for x, and x is just the usual random walk on this graph. So let me just describe this informally. Maybe these are two edges in your graph. Let's call them x and y, and you know they have a positive weight lambda xy. If you don't want to think about weights, just imagine that lambda xy is equal to 1, and then you know, so there may be more edges emanating from x, and you know, if the random walk at some time is in x, then the walk will jump to y with a probability that's proportional to this weight. Okay, so this is a very general setup. So let me just, give you a few examples. So of course, one example of interest is when you have, some lattice, for instance, the Euclidean lattice, and here the walk has to be transient, so that would be d greater or equal to 3. Then, of course, you could think of things which are kind of triary, things like this. This is maybe another class of examples. And finally, there's also other examples, so things like, for instance, fractal graphs. So for instance, you would take your favorite fractal, say, for instance, this Sierpinski gasket. So it turns out this thing is actually, the walk on this is not transient, so maybe cross it with z so that it becomes a transient. And if you spend too much time in Switzerland, then you know this graph is named after some famous chocolate brand that I won't mention here. Okay. All right. So these are just some examples of things that fit this setup. And okay. So when I say low dimensions, I should say low transient dimensions. And of course, you know, for critical phenomena, which percolation is one example of, when the transition is continuous, these low transient dimensions are, in a sense, the hardest ones. Okay, so you have this this random walk. So I will denote its law by. So let me be pedagogical. So px will be. Single bar x will be the law of this thing when it starts at x. And so because it's transient, I have a Green's function, g of xy, which for a probabilist like me is just the integral of the probability starting at x, at time t you're at y. Okay, so this is for x, y, and g, and by transients, this is finite. Okay, so so far, so good. So now I want to talk about, so forget about this for a minute, I want to talk about the Gaussian free field. Maybe I can still squeeze this here. So we've seen actually the Gaussian free field in Felix Otto's talk already. So So I will denote the law of this free field by this double bar P. And so, so I want to define the free field on this graph G. And my life is a little bit easier than Felix's because, so first of all, I'm on a lattice. So that means I have a UV cutoff. I have a smallest distance, which is 1. So this was the, the continuous setup, the K, the wave number less than or equal to 1. And because I'm in transit dimensions, I don't need an infrared cutoff, right? I don't need to put the thing in a box and put zero boundary condition. I can immediately define it in infinite volume. So I really have a field here which is indexed by my graph. And so this is just the Gaussian field, which has mean 0 everywhere, and covariance given by the Green's function of the random walk I wrote up there. Okay, so this is called the Gaussian free field on G with mean 0, if you must be precise. Okay, so so far so good. So I should have drawn this thing in purple as well. Okay, so now I want to study percolation. And so percolation, what? Sorry? Oh yeah, sorry. So thank you. The weights depend on x and y only through the unordered pair. So this is indeed symmetric. Everything is reversible. Thank you. Okay, so so I want to study percolation, and so let me give myself a parameter h, which you can think of like a temperature, but I think of it as a height. And so the simplest version of percolation that you can do for this model is the following. So imagine my graph is down here, so I'm drawing it continuously, but of course it's discrete. And here I'm drawing my field, which is scalar, it's real valued. So I have a field at every point, so I have this kind of random landscape, something like this. And so I want to study a percolation problem. So what you do is you fix some given height h, so maybe I fix it here. And then, so this is kind of a barrier. And then you basically, so my collaborator Alex Divitz has a very nice intuition on how to explain this. So you flood this landscape with water, okay? So and you flood it until height h, and you look at the mountaintops that are left on top of this flooding mechanism. So you look at what are called the excursion sets, which are all the points where the field exceeds value h. And of course, if you cut off at large height h, you might expect that you will see only small mountaintops. But if you decrease h, so this is real valued, you might expect that at some time some infinite connected component emerges, and that's a percolation phase transition. So so if you're already lost, which I hope you're not, but if I had replaced my Gaussian free field by just independent Gaussian random variables, this would just be Bernoulli side percolation. Okay? So the only difference between this model and your very familiar Bernoulli percolation is that the mechanism by which I decide to close or open vertices is not governed by independent randomness, but it's, there's an underlying correlation structure which is induced by this Gaussian free field. Okay, so this is a model which was introduced by Lebowitz and Saller in '86, and so there was one more paper which I will mention soon, and then it lay dormant for a while, and somehow in my thesis, so this was a paper with Snitman, it got resuscitated to some extent. So there's a nice story there. There was a birthday conference for Leibovitz, so this was not, c'était pas un hasard, it wasn't.
Sorry. Molchanov and Stepanov also had some paper.
Yes, but Molchanov and Stepanov, they studied something which is closer to Bernoulli percolation because they studied fields which are short-range correlated. But yes, indeed, this was also around the same time. Yeah. Okay, so I'm not going to give you the full overview of works, and then so here there has been a lot of developments recently. Okay, and so this is possibly the simplest percolation model you can define. It's not going to be the one that I'm going to discuss today. What I'll do is a slight variation of this model. I mean, it's a slight variation, but it's an important one because it, as you will see, adds integrability to the model. So what I'm going to do is not quite this. It's going to be a different way of generating a random subgraph. So what you do is, given the free field phi, so this will now be a percolation model on edges rather than vertices. So you keep the edge xy, which is unoriented, so independently given phi, with probability 1 minus the exponential of minus phi x minus h, positive part, times phi y minus h, positive part. Okay, so what is happening here? So in this model V2, it's actually harder to percolate than in V1. If you want to keep this edge here open, well, first of all, you must have phi x and phi y bigger than h at the endpoint. So you must be in this situation because otherwise you will keep the edge with probability 0. But on top of this, there is kind of a quench disorder, and there is this probability, or rather the exponential probability, to still delete the edge. Okay, so now as to why this particular disorder plays a role, so you are all well-trained probabilists, or analysts, or whatever, so here you will most likely recognize a probability that you know. So this is nothing but the probability that if you take a unit interval, 0, 1, so 0, represents x and 1 represents y, and if you fix two endpoints, so let's say this is phi x and this is phi y, then the probability that I wrote there is nothing but the probability that the Brownian bridge between phi x and phi y stays above the barrier h. So what's happening here is that you are, instead of looking at the, so let me draw, some example. This is my graph, a piece of it. So instead of looking just at the free field on this discrete graph, you are actually adding these one-dimensional intervals, and this is just a way to rephrase percolation of the Gaussian free field on this continuous extension of the discrete graph. But it's the same. I mean, you could also define this as the excursion sets of the free field on these on this metric extension. Okay, so yes.
I was expecting the length of the continuous interval to be lambda. It's not.
Yeah, it is, but I'm dropping some things on the other. Yeah, maybe it should be 1 over 2 lambda xy. Yes. And maybe I should rather look at the density of the Green's function with respect to the measure of lambda, which would be more natural. But that's also it. All right, so this is my percolation model, and I'm going to call, or maybe I can actually write it here. I'm going to call, for lack of a better notation, E bigger than H. So these are going to be the open edges for the parameter H, which is this parameter here. in model 2. Okay, so I'm mostly going to discuss this during the rest of this talk, although I'll make occasional mentions of this model 1. Okay, so I want to investigate the percolation phase transition. So to do that, what you do is you define an order parameter. So if you were doing spin systems, this would be, for instance, the magnetization. In percolation, it's the probability to connect to infinity or to have an unbounded cluster. So pick a point in your graph, call it 0. And the order parameter will be, so I'm going to call it zeta of h, which is, so I will denote this, I hope the notation is clear, the probability that 0 is connected to infinity using a path of only open edges. And because I'm lazy, I'm going to drop this e and I'm just going to write bigger or equal to h, but that's what it means. And if you want to be formal, this is just the probability that something that you might call the cluster of 0 at high h is unbounded. So ch here is the cluster connected component of this point that you have chosen in this random subgraph. Okay, so this, by choice of my parameters, if h increases, I have less and less open edges, so this is actually a decreasing function of h. Okay, so if you imagine some sort of percolation transition, you expect to have a supercritical regime where you have a percolating cluster when h is sufficiently small, and then when you make h large, it will eventually disappear. So, so here is the first theorem. And again, I stress so far everything is true on any transient graph. So maybe I say it. Any of the examples up there, for instance. So if you look at negative heights, so for all h less than 0, actually this order parameter is positive. So you have percolation. Okay, so if you put 0 here, then here you are supercritical. Okay, so so maybe a few words about this theorem. So remark. In fact, Alexis yesterday already proved this in his talk, if you paid attention. He didn't exactly formulate it like this, but it's implied by some of the things he said. So, so for model V1, so the analog of this for V1, which is weaker statement. So this was proved by Brickmont, Lebowitz, Mess. So this was another of these papers from the 80s. And so this is a beautiful argument. It's an indirect argument. It's a few lines which tells you that it's too costly for the Gaussian free field not to percolate at negative levels. And I stress this, it's important because we don't actually have so many good examples of things that percolate in dimension 3 or higher. So this is one example where this is easy. There is no Pyard's argument involved in proving this. And in fact, you know, if you are a percolation aficionado, so if you've heard about recent work of Hugo Duminil and collaborators about how to prove a PC less than 1 using the Gaussian free field, at the end, what they use, the structure that percolates that they use is exactly this GFF at negative levels. Okay, so this was for model V1, and the argument doesn't immediately imply percolation for V2 because their percolation is harder, but of course we know better, so we now also have a direct argument that explains why you must percolate at negative levels, and this goes under the name of so-called, I mean, we've seen a few of those. So this is a Raynight a type identity, and in this specific context, it tells you that you can actually embed a copy of an interlacement inside of this set of open edges when H is negative. And so this guy is a percolating set. This was this soup of random walks arriving from infinity that Alexei was telling you about yesterday. And so a fortiori, this guy percolates too. So it percolates because inside of it there is an interlacement. Okay, so the specific Raynight identity that you're using here is actually due to Snitman from 2012, and then due to Lupu from 2016. And I maybe forgot to say, but I aimed to say it, and I will say it now. So this version 2 of the model, this is following, I mean, he didn't exactly look at the free field, but so I call this a la Lupu. So the story of the metric graph is an old story, even in probability. For instance, the old Carne-Varopoulos bound Varopoulos proof used the metric graph. But in the context of free field and loop soups, it's really the merit of Titus to have somehow introduced this object in this context. And his original motivation was to recover a sign from an isomorphism theorem of Legendre, but this is an idea which has somehow led to many advances. Okay, so okay, very good. So actually, the a la Lupu, it's the same paper that I'm mentioning over here. Okay, so so now you know that in model V2, which is the one we are mostly interested in, for negative levels you percolate, and you could actually use my work over here to conclude that if H is very large, you do not percolate, because what we show, I mean, the main thing we show in this paper was that for model 1, you don't percolate when H is much bigger than 1, but because it's hard to percolate in the second one, a fortiori you don't percolate in the second one either. Okay, but here things are actually much nicer. So, so here is the next theorem, and I'm going to call this continuity, and I will explain why in a second. And again, so far, you can, what I'm going to say is true for any transient graph. So it turns out that for this V2 model, if you look at the cluster of the origin at height 0, so 0 is the next height you're interested in, right? We've already covered all negative H. And if you look at the capacity, so this is some scalar observable of this cluster. Usually in percolation you look at maybe it's the diameter or the volume. In this problem, it turns out that the capacity is an interesting quantity. I will define the capacity in a second. So this is finite P almost surely. Okay, I'll venture into discussing why I'm calling this continuity in a second. Let me just preclude this by recalling what is the capacity. So, so this is just the usual capacity associated to this problem, right? So we have a random walk. It has a generator. There is an associated Dirichlet form, which is, formally somehow the exponential weight that you pick up in this probability, and the capacity of some set K. So K here is a subset of G. Is, for instance, described via a variational problem. So let's say you do an infimum over Dirichlet energy. So here is for suitable F, it's this usual. Okay, so this is a discrete problem. You should think of this as a discrete gradient. This is the quadratic form associated to the generator of this walk. Okay, and so you are minimizing over F, which are bigger than 1 on K, for which, of course, this energy is finite, and which may be 10 to 0 at infinity. Okay, so you know that at height 0, this cluster of your favorite point has finite capacity. And so let's discuss a bit what this means for our percolation problem. So now I need to start making some assumptions on my graph, but so far I'm only going to make a very mild one. So imagine, for instance, that the Green's function is uniformly bounded. So this is true, for instance, if your graph is transitive, because then g of x does not depend on x. So if this is true, then this theorem 2 implies that theta of 0 is equal to 0. And that's simply because under this assumption, you can deduce from the fact that the capacity of a set is finite that the set has to be bounded. Okay? And, well, this is an important piece of news, at least if you are a percolationist, because you knew that over here theta was positive, and now you know, and you can actually easily show a continuity in this regime, and now you know that here, exactly at the threshold where you couldn't say anything anymore, theta is 0, and then by monotonicity it has to be 0 over here. So what this means is that actually in this model 2, on a very large class of graphs, the critical point is always 0, and moreover, at criticality, you don't percolate. So if you know a little bit about critical phenomena, for instance, if you're on Z3, well, that's $1 million question for Bernoulli percolation. And here it somehow comes out of this capacity observable, which is in fact an integrable quantity. Okay, so I will mention that more is actually true. So still under this condition, you can actually say more than what I wrote here. This is what you can say on any transient graph. But under this mild supplementary assumption, you can actually really compute the tails of the capacity of this observable. And so the probability that this is bigger than t, and I'm going to get the prefactor wrong, but so this asymptotically behaves like pi squared g at the point you have fixed times t to the minus 1/2. As t tends to infinity. So this, by the way, is so all the work that's so this is due to Alex Drewitz from Köln, Alexis Prévost from Geneva, and myself, and this is from a couple of years ago. All the results I will mention from here onwards, which involve myself, is always in combinations. So it's going to be DPR, and that's what it means. Okay, so you really have this integrable quantity under mild assumptions on your graph. So let me briefly mention some history of theorem 2. So now for specific classes of graphs, this was, so here it holds on, say, any transitive transient graph in great generality, for instance, for all these assumptions. So on ZD, for d greater or equal to 3, so theorem 2 was first proved, I mean not theorem 2, but rather theta of 0 equals 0, was proved by Lupu in his initial paper. So, so he proved it using a wonderful formula. So here is a theorem due to Titus, Lupu. So when I refer to Lupu's formula in the sequel, this is what I mean. So again, this is true on any transient graph. And it tells you that in this model 2, if you look at the 2-point function, so probability to connect 0 and x at height 0, then this also has an explicit formula, which is 1 over pi arcsine of the Green's function between 0 and x divided by the diagonal ones. So he proved this in his paper, and then if you know that the 2-point function is for any x, and for instance on ZD this will decay, I mean the arc sign near 0 is linear, so you can forget about it. This decays like distance to 2 minus d, so the 2-point function goes to 0. And from this, you would like to conclude that you don't percolate, so this works well if you have uniqueness of the infinite cluster. So let me just briefly show you how this implies that you don't percolate. Well, so if you use uniqueness, which you do have, I mean, he proved it, but you have it typically on amenable graphs like ZD, but for instance on trees it's no longer true anymore, so this argument wouldn't apply on the tree, what I'm going to say now, even though this formula is true. So you can say that, you know, theta of 0 squared, which is, I mean, you don't actually need translation there, maybe theta of 0 times theta of x, so this is the probability that x is connected to, let me write like this. So this is the bounded using FKG by the probability that 0 is connected to infinity and x is connected to infinity. So it looks here like I'm using translation invariance, but in fact you don't need it in the argument. So this is just the FKG inequality. And now if you have uniqueness of the infinite cluster, then you know that if 0 is connected to infinity and x is connected to infinity, then the two are connected together. So this is 0. I'm looking at height 0. Okay, and this by the formula tends to 0. So this is how this implies non-percolation if you have uniqueness. So here I use uniqueness. Okay, so this was Lupu on ZD. Then there was independent work by Snitman on trees. So this was well, and then we did this thing which somehow subsumed these results. Let me mention that, so this will be the last time I go back to model 1, and then I promise you can forget about it. So this is different than model 1. So some time ago, we proved, so this is still the DPL gain. We proved that, so for V1, actually, the corresponding order parameter at height 0, so the probability that you have an unbounded sign cluster, is actually positive. So the critical point for the model V1 does not sit at 0. And that's okay, because the value of a critical point is actually not supposed to be a universal quantity. Okay, so this is just, in fact, you even have this for small epsilon. So this was some number. Okay, that's just a little side comment. Okay, good. So now we know already some things. We know that our phase transition is continuous and that the transition point is 0. So the next order question is to try to understand more quantitatively how the connectivity function behaves. So this now brings me to this one-arm probability that I have in my title. So, okay, so I'm going to focus on this specific observable. Okay, so let me call it theta h tr of r, for instance. So r here is a large radius, say bigger than 1. H is my temperature or my height. And this thing is essentially just a quantified version of this order parameter. So it's the probability that my point 0 is connected to distance r So here PR is a ball of radius r in, say, the graph distance for simplicity around 0. It's a probability that you have a connection above level h, and the truncation means that I add the requirement that 0 does not connect to infinity. So, so this, owing to this truncation, is actually a quantity which should be small, i.e. tend to 0 when r tends to infinity for any value of h. And in fact, so of course when h is negative, if I don't put this, then as r tends to infinity, this will converge to theta of h, which is positive. So this truncation helps make this probability go to 0, but at the critical point and in the subcritical regime, you don't have an infinite cluster, so you can safely remove this when h is greater or equal to 0. And so in particular, at criticality, for h equals 0, I'm just looking at the probability to connect 0 to the large distance r. Okay, so the question which I want to tell you at least a theorem about, but ideally also some ideas of the proof, although starting to have second thoughts about that. Okay, so the question, vaguely speaking, is about the behavior or the decay with R of this truncated two-point function. So, so to answer this now, I'm going to make significantly more assumptions on my graph. So from now on, if you want to be very concrete, just think about ZD. But it's important also for the purposes of universality to keep track of what you are really using. And here, one of the nice things is that you don't really use much of, say, for instance, the lattice structure. All I'm going to need are the following, so assumptions on G. So here they are now. I'm going to keep some technical things under the rug, but they are mostly two ones. So there is a volume growth assumption, which tells me that balls in my graph, say in the graph distance to make it simple, although that's can be generalized, and there is some good reason to generalize this. So you want these things to grow like r to the d. So this means you have two universal constants bounding the cardinality of this from above and below by r to the d, and this is uniform in x. So I'm being a bit sloppy here in my okay, and so this is somehow an assumption on the geometry of the graph. You have to be amenable, so you know ZD is an example, and the other assumption is analytic, and it's an assumption on this Green's function, on the resolvent of the Laplacian, and the assumption is that the Green's function decays like the distance between x and y to some power, which I'm going to call a. So this brings into play d, which is in some sense a dimension for your graph, and a, which is the decay parameter on the Green's function. So I want to stress, so for instance, if you take ZD, then a is of course d minus 2, as you all know. But there are examples such as this one here, where actually the walk can be subdiffusive, and a could be larger than, I mean, this 2 could be a larger number. So 2 is the usual 2 from a diffusive scale.
The implied constants are uniform.
Yes, yes. And everything depends on these constants, yes.
Are you mentioning the graph distance with the weights?
Yeah, so the graph distance was more about the fact that, for instance, if you look at something like here, where you're a product of two graphs, then actually the graph distance is not necessarily the most natural thing, because you might, for instance, here in the z direction you will be diffusive, and in the Sierpinski direction you will be subdiffusive. So the natural distance is to capture the evolution of the walk is not just the graph distance on this product. but it's a technical thing. Don't.
So for the Sierpinski, is it small on a slice?
No. You just. I mean, it's a I mean, in some sense, the comparison is polynomial, but you need to make up for the fact that one diffusive scaling is not the same as the other. That's all. And okay, maybe let me mention, since people are seem interested in this. So these things do not grow out of thin air. So there is fantastic work, which probably the older ones of you know, and maybe some of the younger ones too. So these are very natural assumptions. There is a community of people. So some of the names, Salov-Kost, Grigorian, Telks, and I'm forgetting many, but the particular papers I have in mind are two papers by Sasha Grigorian and Andras Telks. And they tell you that, so at least when the graph distance, these two assumptions on your graph are equivalent to two-sided subdiffusive bounds on the heat kernel. Okay, so this is actually equivalent when this is the graph distance. So this is Grigorian Telks from the turn of the millennium. So maybe 0.1 or 0.3, I don't know, but if you Google it, you will find it. To the fact that if you start at x and you look at the probability that at time t you're at y, so if I call this, let me parameterize, I hope I'm going to get this right. Alexi, did you correct me? So let me parameterize this as d minus beta, and this says that this is equivalent to having heat kernel decay, which is going to be, so it's going to be minus d over beta, which could be 2 or it could be larger than 2, and then there is e to the minus, so here it's up to constant, and there's a constant here, there is also one here, and here it would be d of xy to the beta over t to the power 1 over beta minus 1. So in some sense, what we do in this percolation thing is some analog of this result, but for a different quantity, which is not the heat kernel of the walk, but rather this percolation function. But the result that I'm going to have just time to state in a theorem now is basically an analog, if you like, of these heat kernel estimates, but for this percolation problem. So of course there is a big difference here, which is that this thing is attacked using classical analytical techniques, and here this has nothing to do with these techniques of functional inequalities, etc. Okay, so let me come to my theorem. So to state my theorem, I'm going to introduce two numbers for simplicity, which I will call 2 over a, and a is this exponent here that you have given yourself. So, okay, so I'm interested in the decay, of this truncated radius observable. So what can we say about the decay based on what I've written so far? So we can say some things. So this looks relatively innocent, but actually it's not. So if you want to have a cluster around 0, which extends all the way to distance r, so this is r, then of course this is implied by having the whole box open, and it implies that you will have at least some sort of filamentary or one-dimensional connection to distance r. So this is all, let's say, above 0, or more generally above height h. So, so what does this relatively naive set of inclusions imply? Well, it implies that if I look, so I'm looking at the critical height now. So this is bounded from below by some small constant times r to the minus 1 over rho. So why is this? Well, okay, so I prefer to think about the opposite inclusion. So if you don't have a connection to distance r, then your cluster is at most a box of size r. So the capacity of your cluster is at most the capacity of a box of size r, but the capacity of a box grows like r to the a. And the tail of the cluster capacity, which is here, is this to the power minus 1/2, and that's exactly a convoluted way of writing this. I'm using 1 over rho because this is the terminology that physicists usually use. So, so this is just what you can get out of the integrability of the capacity observable if you're interested in the radius instead. And then there is the same spiel on the other side. So now you're going to compare to the capacity of a line, and now you have different cases because the capacity of a line can behave in different ways. And if you do the thing correctly, you'll find that this is bounded by a constant times 1 over a function which I'm going to call square root of GA of R, and GA of R, so the square root is this square root, and GA of R corresponds to the capacity of a line of length R, and so this is grows like R to the A, so it's comparable to a box if A is less than 1. So this is the case where somehow you're in dimension between 2 and 3, so you're in very low dimension. In dimension 3, which corresponds to A equals 1, it's not quite R to the A. You already lose a factor, which is logarithmic, so that was the log from Alexis' talk yesterday. And when A is bigger than 1, it gets even worse. This is just linear. So there is a mismatch that starts to happen as you cross A equals 1. But you see that even this, so for instance in dimension 3, even this naive approach of comparing a box and a line, you know, which in terms of percolation are two very different things, almost gets you the right answer. I mean, it gets you the decay of this up to a fudge factor, which is logarithmic. Okay, so this, these bounds, they were actually, yeah, let me mention this. So this is all using the capacity observable. So on ZD, this, these bounds here, I have until quarter past, right? That's, yes, so that's perfect.
Maybe
So
just leave positive time for questions.
yeah, we can discuss over coffee. Yeah? Okay, I started a bit late too. Huh? So,
You asked for
so on ZD, this was first proof in a paper by Ding and Wirth from 2020, using a different approach, using a martingale approach. But in fact, it follows, and it follows in greater generality as described here, just from the integrability of the capacity observable. So then there is more results. So in high dimensions, and still only on the lattice, so this is for D bigger than 6. Yeah, 6 is, you know, you see immediately 6 should be the upper critical dimension because the 2 point, where is Titus? Up there, the 2 point on ZD decays like distance to 2 minus D, so your Eisenman-Newman condition that you know and love is satisfied when you're in dimension larger than 6. So, so there was a paper by Wendelin Werner who started to exhibit mean field behavior in these dimensions. And he also made conjectures about lower dimensions, about scaling limits. And then there was somehow picking up on this work by Kai and Ding. So this was from last year. And what these guys proved is specifically that, so this is on ZD for D bigger than 6, you have mean field behavior. So you have your R to the minus 2, independently of dimension. And there is another work by Ganguly and Nam from this year where they basically looked at the random walk on this thing, and they did a version of the Kosma-Nachmias result in this context, so where they proved this Alexander-Orbach conjecture. So there is some sub-diffusive random walks here as well. So this is also, this is even from this year. Okay, so now we get to the theorem. So here's the theorem. So this is still DPR. And there is a paper from late last year and another one from earlier this year. So this was in May. And May will be important. I'm just kidding. So the statement is the following. So if A is less than D over 2, so this includes, so A and D are these two numbers that you see here, and it includes, for instance, the case Z3. Then, so we can say the following. So for the critical, well, I can write a truncation, or I can just forget about it. It makes no difference. So this indeed decays up to constant. Sorry? Theta, yeah. Merci. Did I make the mistake?
Yeah, the previous walk.
My mind got a little lapse. Okay, some people are paying attention, that's good. So the lower bound is actually sharp, so this lower bound was already there, but actually there is no correction. So this is for all R. So this is critical because it is at height h equals 0, and then there is an off-critical result. So this is now the question of when you start to look at a height which is not exactly 0, and you compare to what happens at height 0. So here physicists will tell you that if you have, second order phase transition, continuous phase transition, you expect that there is some characteristic length scale psi until which the two probabilities are comparable, and then you start to realize that you are not at the critical point and you start to decay faster. And so, so this is what I'm going to write here. So the logarithm of these two quantities, and this is true for any h, well, let's say less than 1, it doesn't matter, and for any r. So this is bounded by a small constant, a big constant, sorry, times GA. So GA was this function that I defined there, which governs the capacity of a line of R divided by Xi, and it's bounded from below, so maybe I write it here, by small constant times this. And so what is Xi? So Xi is this infamous correlation length, and Xi in this model is just h to the power minus nu. Okay, so what this is telling you is that at criticality somehow, in terms of capacity, the behavior is morally governed by the capacity of a box. And as you start to go away from criticality, the decay is rather measured in terms of the capacity of a line, which is this decay GA. And so one word to connect to Alex's talk from yesterday, so this kind of off-critical decay is exactly of the form that he was stating yesterday in his theorems, and the sort of first passage percolation techniques that he developed, among others, is used crucially here to get this off-critical decay. Now, I just want to, so I'm not going to have time to say anything about the proof, but I do want to mention that, I mean, make no mistake, this is, what this is telling you, for instance, at criticality is that in terms of the capacity, your critical cluster is indistinguishable from a box. But the critical cluster, I mean, you saw pictures yesterday, is far from being a box. So for instance, if you look at this decay, so this is telling you that if you think about the fractal dimension, for instance, you need to multiply this by r to the d, and what you get here, I think in dimension 3 will maybe be 2.5 or something. So this critical object that you have still has the intermediate fractal dimension, which is strictly less than d. Okay, and then the last thing I will mention, so there is even more recent work. So this is, again, two people I've already mentioned, Zhenhao Tsai and Jian Ding. So this is 24, but it's June. So there was a friendly competition, but no one knew. So they actually managed to prove, they extended this critical result up. So this, so the lower bound was known, this upper bound here, so they proved it on ZD, and so they proved it for all D between 3 and 5. So up there you have it for dimension 3 on ZD. I didn't include dimension 4, although I should give ourselves credit for what we are able to do. So you remember in dimension 4 you already have a discrepancy. So here you will have r to the minus 2, and here you will have r to the minus 1. And we almost got the, so this was the first paper, we almost got the r to the minus 2. What we had is here, some big power of log when in dimension 4. But there is a reason, which I won't have time to explain, that our method, at least in its current form, stops in dimension 4. And so what they did is they removed this log in dimension 4, and they even proved it in dimension 5. And now they have, so they also have a result on Z6, which is the only remaining one, and there is a fudge factor, which is, I think, square root of log r, maybe, let me put it, log r to the 1/2 plus epsilon. So it's subpolynomial, but there is, it's still there, and in dimension 6, of course, you might expect that the lower bound is not completely sharp. Okay, so yes, so I will stop here. Thank you for your attention.
Is the non-amenable one easier or harder than these assumptions?
So, sorry, what's your question
So
again?
you've done it for the amenable.
Yeah.
Is the non-amenable trivial, or is it very difficult?
Well, I'm not a friend of the word trivial, so you're not going to get this out of my mouth. But it's, I think, fair to say that, so it has been looked at less, that's for sure. It's probably easier, that's fair to say. Although I'm thinking about easier cases. For instance, if you're a tree, then this model is like a branching process with infinite types because you have real value. So you get into the realm of another set of techniques, which is actually the thing that Snitman had used when he was looking at this problem here. One thing which I think is accessible and which people have started to work on, including Guillaume, who was also mentioned in the previous talk, is so for the harder model 1 to look at the problem in high dimensions or on trees. Yeah. But I wouldn't say, I mean, even for usual population, these high dimensional results, they are now established, but they're still difficult.
Some questions? Okay, so questions on the proof from the back. Thank you very much.
much.